Hello, everyone. Welcome to our webinar on heat recovery and energy efficiency. Today, we will cover quite a few topics. The main points will be economic benefits related to energy recovery in industry and HVAC applications, BPHE advantages. We also urge you to please follow SWEP's LinkedIn page. Here you will see future webinars that we hold, and this will give you a chance to register for any of those you are interested in. My name's Summer Evans. I'm Market Communications Specialist for SWEP. We appreciate you spending part of your day with us today. Now I will turn things over to Mr. Adam Dahlquist.
Wow, thank you very much, Summer. Thank you. So my name is Adam Dahlquist, working as a SWEP as a business development manager. And I will share my screen. Monitor 2. Here we are. Sorry. As a business development manager, first of all, I would like to present what is SWEP. SWEP is a brazed plate heat exchanger expert company. We were founded in 1983 in Landskrona, Sweden. And since 1994, we are part of the US-based Dover Corporation. That is a publicly traded company on the New York Stock Exchange. SWEP has about 1,000 employees worldwide, serving about 16,000 customers who are using about 3.5 million brazed plate heat exchangers annually. SWEP has 5 factories, one in Landskrona, where is the headquarters, one in Košice, Slovakia, one in Suzhou, China, Kuala Lumpur, Malaysia, and here in Tulsa, Oklahoma in the United States of America. SWEP is certified 14001, 9001. We use Six Sigma for quality work. Our products are AHRI certified, and we have third-party pressure vessel approvals from more 30 approvals that I can mention right now, but we'll look into that a little bit later. This webinar is about energy efficiency and heat recovery, and whenever SWEP sees that energy is wasted or not recovered, we would like to challenge that status quo. The motto of SWEP is to challenge efficiency, and how brazed plate heat exchangers can make your system more efficient and recover more energy is what we want to discuss here today. So the backdrop of this is that in almost all production processes, there are production processes or auxiliary equipment that produces energy in addition to what they're supposed to do. This could be in the form of steam, warm water, or air, but rarely is this energy recovered and redistributed to be used again. It's normally just wasted. What we like to show here is that there is not only an environmental benefit, but also an economic benefit of recovering and redistributing this energy. And we also would like to show that the brazed plate heat exchanger is a very efficient and cost-effective core component of energy recovery in industry and HVAC, both for existing and future installations. So let's start with a generic production facility. There is the industrial process plant, there is the offices, and there is the changing rooms. And we get the utilities, electricity coming in. We have the boiler. We have the comfort chiller to keep the temperature regulated for the people working there. We have the air compressor, air dryer, to make for doing what pressurized air is doing. We have the process chillers, cooling the process itself or any auxiliary system, in this way a hydraulic power unit or HPU. Before we go there, so in this very basic setup of machinery, we do see that the brazed plate heat exchangers can be found as evaporators and economizers, and sometimes even condensers in the comfort chillers. We see them as oil coolers and air coolers in the compressors. We can find the brazed plate as an air dryer inside the air dryer machine, so it cools, dehumidifies, and reheats the air in an air dryer. We have them as a evaporator condenser in the process chiller. We can see them as an oil cooler in the HPU. So already now there is a lot of places where a brazed plate is used for everyday industrial and HVAC operations. If we continue to build this industrial application with a little bit more complications, we see that a factory might have a genset for electric production, so that they have redundancy in electricity in having electricity. Gensets are much more common in the United States than combined heat and power. But we will see the advantages of having a CHP kit mounted on a genset. In this case, when we start now, we have a cooling tower that is connected to the compressor and the genset to take away the heat, just to so to say throw it away, which is a fairly common way. Since they are connected to a brazed plate heat exchanger, we see that they are using a filter to reduce the amount of fouling particles that are around in the system, and we will look into that a little bit later. What are the recommendations for filters when using a brazed plate heat exchanger? For the process chiller, there is a dry cooler. Since it's a closed system, there is no need for the filter. And at this point here, I would like to, so to say, pause a little bit and just see. This is a fairly typical installation. There is a lot of applications. Everything might be as energy efficient as it can be. Each producer of the machinery have worked to make their system efficient, but there is still a lot of waste since there is no energy recovery. And now that is what we will start to build into this system. What we'll start with actually is the free cooling. So what is possible to do is that if the ambient temperature is below the temperature of what you need to cool the process, and that could be of course industrial process, could be an IT server hall, something that needs cooling even during the cold parts of the year. What free cooling means, it's that it's possible to have the dry cooler take directly the cold ambient temperature and cool the inside, and just closing off the process chiller, not operating the chiller at all. What you want to do then is to separate the outdoor system from the indoor process, because the indoor process can be very sensible, and you don't want to have any, you want to increase the redundancy of separation. And there, a brazed plate heat exchanger is a very efficient tool, being compact, cost efficient, and highly thermally efficient. We will look into that a little bit later in detail. Let's continue to build here. So now we have intermediate brazed plate heat exchangers to collect and redistribute the heat for energy recovery. So where can we get heat from? Well, we can get it from the normal chillers. If we're using the superheaters, we can get temperatures at pretty high values, 140 to 180 degrees, which is of high value. From the air compressor and the genset, or combined heat and power system at this point, we can get also energy at high temperatures of high value, which will again look into more in detail later on. So now we see where we can collect energy. Where can we use it? We can this energy has only value if it can be put to use somewhere. So where can the heat exchanger redistribute this energy? And a standard, a very simple way is that if we have a boiler that needs to heat water, create steam, by preheating the boiler water, we can directly save that burning gas by preheating it from the energy that we recovered. Or we can, maybe the energy is used directly into the process, so we can heat the process fluids directly with this energy. Or more, we have more alternatives, even more. We can just use the energy to heat the premises, the space heating. By using a double wall heat exchanger, we can create tap water so that the showers are running for free. And there are even more ideas here. I mean, there could be snow melting potential. There could be a swimming pool in the area, or possibly there is a neighboring process plant, your neighbor, another company, but still adjacent. Maybe they need energy that you can sell to them. There is another possibility that that energy can be redistributed, not within your ecosystem, so to say, what we see here, but to the next door neighbor. What if you have a lot of waste energy or waste heat? There could be an interesting system, is an ORC system, organic Rankine Cycle. Always hard to say, easier to say ORC. That kind of system takes, so to say, large amounts of energy or heat and changes it to electricity with its own economic calculation, as we'll look into. And since we now have and if we then also add photovoltaic solar panels, which is also possible to put on here, we have the solar panels, we have the ORC, we have the genset. It could even be that this process plant now have an excess of electric energy, and what can happen, what you might need then is an energy storage. There are different types of energy storage. There is battery energy storage. In the US, Tesla is a very famous battery producer, doing battery storage units. But there is also thermal energy storage, where you typically produce ice when electricity is abundant, and then you use the ice to cool when electricity is scarce. And even regardless if it's a thermal or battery energy storage, brazed plate heat exchangers can be used to make ice for thermal, or to regulate the temperature during charging and discharging of a battery energy storage. So there is many opportunities to collect or redistribute energy, be it heat or electricity, and brazed plate heat exchangers is a core component for all of them. So let's, from this pretty complex image as it is now, let's go and look into details. For the economic calculations, I've been focusing on the US values, average US data for gas and electricity, and I'm using megawatt hours for everything. So according to Statista.com, the average cost per for industrial cost per gas is $10 per megawatt hour, and electricity is $70 per megawatt hour. Interesting to see is that the same data for the EU is gas is almost, is more than 4 times expensive, and electricity is 3 times as expensive. So the economics of energy recovery is even more significant in Europe, but we will look into the data for US for this example. And of course, if you're living in an area where that is not US or EU, please use your data to calculate calculate recalculate the data for your area. So let's start with a CHP. A genset is an engine genset is a large engine that consumes fuel, could be gas or diesel or even petrol, to create electric energy. And that is about 40% of all the energy that you put inside, you get out to electricity. And it's not bad, but if you start to recover energy from the jacket water, from the intercooler, from the oil, and from the exhaust gas, you will be able to use 90% of the total energy that you put in. And to compare compare the genset to the combined heat and power, a 1,000 kilowatt, meaning that it produces 1 megawatt of electricity. A 1,000 kilowatt genset consumes about 60 megawatt hours of fuel every day, and with the data we saw before, that's about $600 a day if we operate it at natural gas. So $600 per day. If we just calculate the energy recovery, this part here, the CHP module, we will be able to recover about 30 megawatt hour per day, which is 50% of the energy cost that you put in. So you can so to say save 50% of your energy running cost by going from a genset to a combined heat and power, if you can recover and redistribute that energy. Air compressors. Here is another low-hanging fruit when it comes to energy recovery. A air-cooled standard air compressor, which I call here an inefficient system, might be a little bit subjective, but you'll see what I mean. Electricity is used to drive the compressors to make the air, and then electricity is also used to drive fans to dissipate the electric, the energy that has become heat. And 10%, about 10% of all electricity used in the industry worldwide is used for making compressed air. However, about 90% of that energy, 90% of the total 10% in the industry becomes heat, because the process of making pressurized air is so inefficient that 10% becomes what you really want, the pressurized air, and 90% becomes heat that is just then dissipated by using cooling fans. So, but if an oil cooler, intercooler, and fluid cooler is introduced, it's possible to recover most of this energy. So in an example here, a 200 horsepower compressor that makes about 800 CFM, cubic feet per minute. That is a fairly large but still standard size of a industrial compressor. It's not as it's something you can still buy from the catalogs, so to say. It will use about 3.8 megawatt hour of electricity per day, which means $270 per day, or $99,000 per year, 24/7, 365. Since this process is so inefficient, we can recover almost all, or 3.5 out of 3.8 megawatt hour of the heat. Since it's heat and not electricity, the value is less. So it's only sort of $35 per day, but it's still $13,000 per year. It's about 10% of the operating energy cost. And as we saw before in Europe, or whenever the cost of heating gas or heating is higher, this one is going to be of a more relative value. But what we have seen is that to install a heat recovery for an air compressor rack has one of the shortest paybacks, and it's typically less than 1 year, because the reason for this is that the the compressor produces so much heat than compared to the pressurized air. Yep, moving on. Heat recovery of chillers and heat pumps. Chillers, they are everywhere. It's much more common to find air-cooled chillers and heat pumps rather than water-cooled. And since they are optimized to operate at a low condensing temperature, because that gives a higher EER or COP, the energy, the temperature of the energy you get out from the condensing energy is so low that it's rarely considered to have any value. However, if the superheater is installed, we can get about 30 to 40% of the condensing energy at a higher temperature. And by using a Brazed double wall heat exchanger, it's possible to take this energy directly and run it against cold tap water coming in and having warm shower water, warm tap water directly. SWEP double walls are certified by PED, UL, NSF 372, and Kiva, among others, to use for tap water. If we take this example here, a 100-ton chiller, again, fairly big chiller, right? But it's an industrial application and it's still within the typical range here. A 100-ton chiller will use about 2.2 megawatt hour of electricity per day. It's $150 in our calculation. The total heat rejection from the condenser is about 125 tons due to the compressor work. So it gives 100-ton cooling, but rejects 125-ton heating. Most of this is at the low temperature without so much value. But with the superheater, we can get let's say 30% of that energy at high temperature, which means 3.2 megawatt hour, and we have $30 per day in value there, and that's 20% of the energy cost. And even if you think, okay, $30, that's not so much money, but it's 20% of the energy that you put in there. And if you think of the factory working and you start to sum up all the different savings you have, there is a bottom line advantage that it cannot be neglected. So let's go to the free cooling, the way we looked before. If you have the baseline for free cooling is that you have a process or a load side that is needing cooling all year around. An industrial process or an IT server hall, data cooling. If this system is in a climate where it can be cool during parts of the year, there's a significant savings potential here. So what it means is that when the ambient temperature is below what the load side is requiring, the cooler, the mechanic cooler, the compressors, and everything that consumes energy that we saw before can be turned off, and the cooling can be partly or completely handled by the outside cooling tower or dry cooler. Since the outside loop is typically operating with glycol, or using, or if it's an open loop, it's not using glycol, but it's more dirty. Either or, if it's glycol or an open loop, you don't want to have glycol into the load side, and you don't want to have dirty open loop water into the server side. You need a efficient heat exchanger that can transfer the energy from the cold outside to the inside. And if the economics here is very impressive. So we say again, a 100-ton chiller, as we saw before, it consumes 2.2 megawatt hours per day. about $150. And since this process requires cooling all year round, so this is 24/7, 365. But if you're able to turn it off, you will save that $150 a day. Of course, not fully, because you still have to have pumps running and other things. But it's going to be, you know, minimum 90% of the operation cost is going to be for free. And the economy of having a free cooling is unquestionable, and the need for an efficient and compact heat exchanger to be able to be inactive during parts of the year, so it cannot be too big. It's taking up waste some space, and you want to have a heat exchanger with low efficiency, low footprint, and high efficiency to transfer the coolness from the outside to the load side while protecting the system. And a special discussion here is that the free cooling is particularly common when it comes to system critical or IT cooling. And there are three main types of cooling of an IT system. This is not an IT cooling webinar, but there's the room, row, and rack. Room is when you cool the whole room. Row is the row of servers, and rack is the server rack itself. What the closer the cooling comes to the actual server, the higher the temperature you can operate with, and that is an advantage. Because if you're operating with the more efficient row or rack cooling solutions, you can operate at a higher temperature here into the load side, and the higher temperature the load side can accept, the more you can use the free cooling. So row and rack kind of cooling is very advantageous of using free cooling because you have more days where you can use it. But more in that in a separate webinar. Organic Rankine Cycle. There, I nailed it. ORC. The ORC system is very interesting. It's an old technology, but it's still hot. It uses high temperature waste heat, or high temperature heat, above 160 Fahrenheit, 90 Celsius or something, to drive an expander, or we can say a reverse compressor, to generate electricity. Since the ORC system requires so much energy, it's typically put together with a engine genset, as we discussed before, where you have flare gas that you cannot burn off, or you have to use it in some way, or you have biomass or geothermal, or any other situation where there is a large excess of heating energy. There is a lot of need for heat exchangers, and typically brazed plate heat exchangers in ORC systems. You need it to evaporate, condense, and economize or regenerate the flows inside the system. I'm not going into details how it works. We don't have time for that. But it's kind of, you know, it's an interesting system. And with all of this, it will take energy and transform it with about 10 to 15 efficiency. So it's not amazingly high, but again, if it's operating at waste heat, which is free, this is amazing. So it with about 10 to 50% efficiency, it will convert it to electricity, and commercial systems are available from 35 kilowatt electricity production and upwards. And I'm using Electrotherm by Bitzer as reference here. So an example here, if you have 1,000 kilowatt of waste heat, which corresponds to 24 megawatt hours per day of waste heat, you will be able to produce about 2.4 megawatt hours of electricity. So a tenth in this example, valued at $170 per day. And unfortunately, I don't know the payback for this kind of system. Depends on where you can get the energy. But since the production of this waste heat is electricity and not not so to say just warm water, the economic calculus becomes stronger immediately, since we get electricity and that has a higher value. So a 1 megawatt of waste heat will be able to give you $170 of electricity per day, or 62,000 per year. Those were the main energy recovery calculus I wanted to show you today, and how the braze plate, what part the braze plate plays in these different systems. I would like now a few minutes to go through what is a braze plate heat exchanger and how does it look like. If we just take the basics, the smallest braze plate heat exchanger, BPHE, that SWEP is producing is this one here. Is the size of a iPhone 4, more or less. So it's a palm size heat exchanger with 1/2-inch ports. And the largest one we have is about 4 feet tall with 6-inch ports. All heat exchangers can operate at vacuum pressure. The normal operating pressure is between 450 to 650, depending on model. But we have models that go up to an operating pressure of 2,000 psi for CO2. 100% of our heat exchangers are tested before shipped out. The pressure testing is 1.5 times the max operating pressure. So if it's 450, then it's tested at 900 psi. And after it passes this pressure test, it is then leak test by helium to see if there's any leak inside the heat exchanger. Again, 100% of the heat exchangers. Maximum minimum temperatures, minus 321 to 437. This is Fahrenheit. So it's, you know, from liquid nitrogen, more or less, up to the safe temperature for copper. I would like to say here that copper is the most common. The plates are made of stainless steel, but they are bonded together by copper. SWEP also have an all stainless range with plates and bonding material in stainless steel that has higher temperatures. But since copper brazed heat exchangers are more common for energy recovery, that is what I'm focusing on today. Please contact SWEP if you want more information about brazed plates or all stainless bonded heat exchangers. Certifications, as I mentioned before, HRI, UL, ULC, ASME, CRN, PAD, KHK, etc., etc. We have a lot. Please ask if you don't see your third-party approval that you need, if it's not listed here. The capacity, how much flow one heat exchanger can take, is about, the big one can take about 1500 GPM, but that's just with one heat exchanger. And we have seen that there is economic benefit of modularizing braze plate heat exchangers. So we have up to 16 of these in parallel to operate at a much higher flow with economic benefits compared to alternative solutions. How do we work with creating our heat exchangers? We work with high theta and low theta plates. High meaning high thermal efficiency, high pressure drop. Low meaning low thermal efficiency and low pressure drop. We have products with a large pressing depth and a low pressing depth. High pressing depth means large pressing depth means less thermal efficiency, lower pressure drop. The opposite is true for the tight channels, that is higher pressure drop and higher thermal efficiency. And combining all these differences, we have symmetric and asymmetric plate geometries, where symmetric plate geometries, the cold and hot side, so to say, look the same. And in asymmetric plate geometries, we have one side that is narrow, or meaning high thermal efficiency, high pressure drop, and the other side that is low thermal efficiency and low pressure drop. And an asymmetric heat exchanger would be perfect in applications where gas and liquid meets, like a superheater. A superheater would be perfect with a symmetric plate where gas goes in the wide side and water goes in the narrow side, or an oil cooler where you have the viscous oil going on the wide side and the lighter water going on the narrow side. If you have water to water, you will probably benefit from using a symmetric heat exchanger. So in all of this, SWEP has a lot of different models with high and low theta plates, large and small pressing depth, symmetric and asymmetric heat exchangers. And what you see now is not all of them, but the most common one we have for HVAC and industrial applications. And as you see, if we start with the smallest one with a 1/2 inch, goes through 1 inch, 2 inch, 4 inch, and up to 6 inch in port size. The dimensions are written here. And then for double wall, we have a 1 inch model and a 2.5 inch model. And I would like to point out that the SWEP double wall is a double wall all over the plate. It's a double wall here, 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 and here. Here, 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 here. Wherever you see on a double wall from SWEP, it's a double wall all over the plate. The reason why I point this out is that there are double wall solutions out there that are, so to say, protected around the ports, and that's it. So it's a double wall in the port area, and then it's a single wall, and then it's a double wall again. That is extended protection around the port, I agree, but it's not a real double wall. So if your application requires double wall, please make sure that you're getting a double wall and not a port protected product. Moving on. SWEP core competences. Well, of course, we do the simulation, we do the design, we do the tooling, we verify what we have invented. We are expert in the material that we use to make our heat exchangers. We do our own tools, and we do brazing of the products to bond the plates together, and then we test everything we do. We take brazed plate heat exchanger development and production very seriously, and we would be happy to show you what we can do with it based on your needs. How do you select the heat exchanger? Well, it's SWEP has a simulation tool, SSP. It's available as a downloadable standalone version. It's also an online version. Both are free to use, free to download, etc. However, you need to be registered. You can, if you download it, you will only have a demo version. You have to write down, who you are, your company, if any, telephone number, email, so that we can contact you and register you as our user. Once you have done that, you will get an access code automatically, typically, and which will open up the selection software for your needs. SWEP also have, for, so to say, the more company user, we have a DLL that can be incorporated into your simulation module of your company. Getting the brazed plate simulations directly into your software. It requires some integration from your side, but SWEP will be happy to support you in doing this, and we have several 100 customers doing this already today. And more of a hands-on approach, we also have quick selection guides for different applications that can be used based on regional availability. So a quick selection would be available for US, Europe, and Asia, depending on the applications and typically the products available in the factory or warehouse at that place. And that was the main presentation. Thank you very much for participating. I hope I didn't go too fast. And again, as Summer said in the beginning, if you have any questions, please reach out to us. or to your closest SWEP representative, and we will be happy to go in depth in what we said. But since you came so far, if you're here now, there are some bonus slides. So we have been talking about brazed plate heat exchangers, but why brazed? Why not shell and tube? Why not plate and frame? Well, I will try to explain that with one slide. In a plate type heat exchangers, and especially SWEP, we're using CFD and other methods to optimize the plate design to make sure that it's as efficient as possible. As I showed you in detail before, we have different type of plate technologies creating geometries for optimizing thermal efficiency and pressure drop. And especially in the plate heat exchangers, since the flow is so twirling, we get a turbulent flow already at Reynolds 150, which is very, very low if you compare it to about 2,300 in a straight tube of the shell and tube. And the third advantage that we'll look into now is that the self-containing structure of a brazed plate. Since between two plates, the stainless steel plate and stainless steel plate, we have the filler material, which is typically copper, even though it can also be all stainless, as I said before. During the production process, there is stainless steel, and a very thin layer of the bonding material, in this case copper. When we put this in the furnace, the copper becomes liquid and connects to the contact points via the capillary forces. When the temperature goes down, the copper becomes a metallic glue that makes all these plates stick together. That means that there is no need for any type of frame, bulky frames or anything else that just takes up space and weight. So the heat exchanger is very material efficient, with about 95% of all material going inside is used for heat transfer. So this means that the brazed plate compared to the tubular type of heat exchanger is much more efficient, with more turbulence, more energy transfer per weight, per size, per everything. So for the same efficiency, you will have at least 80% lower weight, at least 80% reduced footprint, at least 80% reduced hole-up volume with a very close temperature approach. And you might ask, okay, why is hole-up volume interesting? It's interesting because the more thermal mass you have inside a system, the longer it takes to change, to update the temperature, to make changes to the temperature. And if we have a lot of energy, a lot of weight of fluid inside here, and there is a change of the temperatures in the process, it will take time before the heat exchanger with a lot of thermal mass will be able to change that, to update that. With a brazed plate heat exchanger being a very small internal volume, it's easier to have a more direct and fast update of temperature control of the process, make it more exact and more direct. If we compare the two plate type heat exchangers, the plate and frame and the brazed plate, since the brazed plate do not need the frame, you will, and the frame is very, very heavy, you will get about a 50% reduction of weight with the brazed plate compared to a plate and frame. We will also have about 60% reduced footprint, not because of the heat exchanger itself, but because since the plate and frame has gaskets, over the lifetime of this product, you have to open it up. You have to be able to get the plates out to change the gaskets. So you have to have a lot of service area. And you don't need that with the brazed plate. It doesn't have gaskets. So if you have like for free cooling, when you have a heat exchanger that is not used for half the year, if you can have a small heat exchanger standing in a corner and not bothering anyone, and then for half the year starts to save a fair amount of money, that is a better economic discussion than having a half a room full of a heat exchanger that is not working for half the year. The recommendations of installing a brazed plate heat exchanger is very similar, if not identical, to any other heat exchanger. We want the heat exchanger to be correctly selected. We want to have turbulence. We don't want it to be over dimensioned to any large extent. We want there to be a strainer, not a filter, but a strainer, to avoid that large chunks of stone or pebbles get inside the heat exchanger to blockage it. But with a strainer, this can be stopped before the heat exchanger so that the heat exchanger doesn't become the strainer. And then water flow control, making sure that water is flowing, because turbulence is the key factor for avoiding that fouling builds up. When it's for an open loop, the recommendations for open loop water is the same for almost all heat exchangers. There are many good open loop installations, but of course there are some bads as well. The water filtration is important for open loop, because there is a continuous influx of small particles, and you don't want that to build up. So for open loop water systems, a filtration method to bleed out the small particles is recommended. And then of course the question would be, yes, but you cannot open a brazed plate heat exchanger. What if fouling happened, right? And what we have seen is that cleaning in place has taken big strides during the lifetime of SWEP. Now cleaning in place is able to not only match but outmatch the possibility for mechanical cleaning. And I mean outmatch in a way of economic sense. Even the manufacturers of plate and frame heat exchangers recommend cleaning in place as the first stop for when fouling hits. The reason being that the economy of closing everything down, having opening up a heat exchanger to clean it out mechanically is such an economic hit of downtime and manpower that cleaning in place is much more makes more economic sense. SWEP cooperate with several different types of cleaning in place providers. Goodway is a US-based cleaning in place expert that we have been working with to make some examples of case stories. One of them was with a multi-stack chiller installed somewhere in the US. It was a pretty big chiller, and it had been operated with poor water quality for some years. So the compressor head pressure had increased 165 psi, which is a lot. It's a lot. So to the extent that the high pressure protection for the compressor started to close the system down. And after about 24 hours of cleaning in place, the whole system returned to factory specification. It was completely restored. So there was enormous fouling, and it was completely restored in one day. And the economic savings of having a clean condenser that it went down from reduced the head pressure of 165 psi, just the saving was $348 a day. The other examples we have here is an installation of a heat recovery in a black water plant of a brazed plate installation where it's black water, it's poop, and even this system was cleaned out and returned to factory specifications. So with these two examples, I hope that you can see that cleaning in place is an efficient way to clean out for different types of application, HVAC and process, you can say, and compare that to having a manpower opening up a system, having it every plate taken out, cleaned, and changing the gaskets. From our point of view, we see that the economic benefits of cleaning place, first of all, avoiding fouling, number one. Number two, cleaning in place are the two most cost-effective ways of maintaining economic benefit of a plate heat exchanger, and a brazed plate heat exchanger being the more compact and cost-efficient of those. So with these extra slides, I would like to hand back to Summer. If she is not there, I would like to thank you very, very much. Goodbye.
Yes, I'm here, Adam. Thank you, everyone. As he said, please contact SWEP directly if you need any additional follow-up information for this. I urge you once again to join our LinkedIn page to follow us to get all relevant updates for products and applications, and also for future webinars that we will have available. Thank you very much.
Thank you.